Nuclear energy mission. Pathway to sustainable power. Energy has always been the backbone of human civilization, driving industrial growth, technological progress, and improved standards of living. As the 21st century advances, the world faces a pressing dilemma: how to meet the ever growing energy demand while reducing greenhouse gas emissions and minimizing environmental degradation. Fossil fuels, once the cornerstone of industrial revolutions, are now recognized as unsustainable due to their finite reserves and contribution to climate change. Amid this challenge, nuclear energy has emerged as a powerful contender in the clean energy race. It provides large-scale electricity with near-zero carbon emissions, high energy density, and reliability unmatched by most renewable sources. Many countries have already integrated nuclear energy missions into their national development strategies, while others are exploring nuclear power as a way to balance energy security with environmental responsibility. This video explores the nuclear energy mission, its history, technology, role in energy transition, challenges, and future prospects, highlighting how it can become a cornerstone of sustainable global development. The concept of a nuclear energy mission. A nuclear energy mission refers to a strategic plan undertaken by a nation or global alliance to develop, expand, and regulate nuclear power for electricity generation and other peaceful applications. Such a mission typically includes 1. Research and development, advancing reactor designs, improving fuel cycles, and enhancing safety features. 2. Infrastructure development, establishing nuclear power plants, fuel processing facilities, and waste management systems. 3. Regulatory frameworks, enforcing safety standards, environmental compliance, and non-proliferation commitments. 4. Capacity building, training skilled workforce, fostering public awareness, and creating academic, industrial partnerships. 5. International cooperation, sharing technology, ensuring nuclear security, and managing cross-border energy trade. These missions are not only about producing power but also about securing a sustainable, safe, and low-carbon energy future. Historical evolution of nuclear energy. The idea of harnessing atomic energy dates back to the early 20th century with discoveries in nuclear physics by scientists like Henry Becquerel, Marie Curie, and Ernest Rutherford. The breakthrough came during the 1930s when nuclear fission was discovered, paving the way for energy release from atomic nuclei. 1942, the first controlled nuclear chain reaction was achieved under the Manhattan Project. 1954, the world's first nuclear power plant began operation in the Obninsk, Soviet Union. 1950 to 70, nuclear energy expanded rapidly across Europe, North America, and Asia. 1986, Chernobyl, and 2011, Fukushima, accidents raised global concerns about nuclear safety. 21st century nuclear missions were redefined with emphasis on sustainability, advanced reactors, and climate change mitigation. Today, over 440 nuclear reactors operate in 30-plus countries, providing around 10% of global electricity. Importance of nuclear energy in today's world. 1. Low-carbon electricity. Nuclear power plants emit negligible carbon dioxide during operation, making them crucial in climate change mitigation. 2. Energy security. Uranium reserves are abundant and geographically diverse, reducing dependence on volatile fossil fuel markets. 3. Base load power supply. Unlike solar and wind, nuclear power is not intermittent and ensures round-the-clock electricity supply. 4. High energy density. 1 kilogram of uranium can release energy equivalent to several thousand tons of coal, making it highly efficient. 5. Industrial and medical applications. Beyond electricity, nuclear technology supports cancer treatment, food preservation, desalination, and space exploration. Major national nuclear energy missions. 1. United States Nuclear Innovation and Clean Energy Goals. The U.S. emphasizes life extension of existing reactors, investment in small modular reactors, SMRs, and advanced Generation 4 designs. Nuclear is seen as a key element in achieving net zero carbon emissions by 2050. 2. France. Nuclear power dominance. France derives nearly 70% of its electricity from nuclear energy. Its mission prioritizes energy independence, decarbonization, and leadership in nuclear export markets. 3. Russia. Global exporter of nuclear technology. Russia's Rosatom plays a central role in supplying nuclear technology worldwide, building reactors in Asia, Africa, and Europe as part of its energy diplomacy. 4. China. Rapid expansion of nuclear fleet. China's mission focuses on diversifying energy mix, reducing coal dependence, and leading in fourth-generation reactor technology. It is currently the fastest growing nuclear power producer. 5. India. Three-stage nuclear power program. India's mission emphasizes energy self-reliance with its unique three-stage program. Stage 1. Pressurized heavy water reactors, PHWRs, using natural uranium. Stage 2. Fast breeder reactors using plutonium. Stage 3. Thorium-based reactors to utilize India's abundant thorium reserves. This long-term strategy positions India as a potential global leader in sustainable nuclear innovation. Key technologies driving the nuclear energy mission. 1. Pressurized water reactors, PWRs, the most widely used design worldwide. 2. Boiling water reactors, BWRs, simplified cooling but with direct steam contact. 3. Fast breeder reactors, FBRs, generate more fissile material than they consume. 4. Small modular reactors, SMRs, compact, scalable, and cost-effective reactors for future grids. 5. Generation IV reactors, advanced designs focused on safety, efficiency, and minimal waste. 6. Fusion reactors, experimental, promising unlimited clean energy, with projects like ITER in France leading the way. Challenges facing nuclear energy missions. 1. Safety concerns. Accidents like Chernobyl and Fukushima fuel public fear. Ensuring robust safety systems is critical. 2. Nuclear waste management. Radioactive waste remains hazardous for thousands of years. Permanent disposal solutions like geological repositories are still under debate. 3. High initial costs. Nuclear plants require massive upfront investments, making financing difficult compared to cheaper renewables. 4. Proliferation risks. Misuse of nuclear materials for weapons remains a global security concern. 5. Public perception and opposition. Anti-nuclear movements often challenge projects, slowing down implementation. 6. Competition from renewables. Falling costs of solar and wind power question nuclear's economic competitiveness. The role of nuclear energy in climate change mitigation. The Intergovernmental Panel on Climate Change, IPCC, emphasizes nuclear as a critical component of low-carbon energy portfolios. By replacing coal-fired plants, nuclear energy could cut billions of tons of carbon emissions annually. Moreover, when integrated with renewables, nuclear power provides grid stability, acting as a reliable base while solar and wind supply variable loads. Innovations for the future. 1. Thorium reactors abundant, safer, and with reduced long-lived waste. 2. Molten salt reactors, MSRs, enhanced efficiency and passive safety. 3. AI and digitalization, advanced monitoring for predictive maintenance and accident prevention. 4. Hybrid energy systems, coupling nuclear plants with hydrogen production and desalination. 5. Nuclear fusion, although still experimental, it represents the holy grail of limitless clean energy. International cooperation and agreements. International Atomic Energy Agency, IAEA, oversees safety and non-proliferation. Nuclear Non-Proliferation Treaty, NPT, prevents weaponization of nuclear technology. Paris Climate Agreement encourages nuclear energy as part of carbon reduction strategies. Global partnerships, projects like ITER, fusion research, highlight global collaboration in nuclear missions. India's nuclear energy mission, a closer look. India's nuclear strategy is uniquely shaped by its resource constraints and ambitions. Current status, about 7,500 megawatts of nuclear capacity, as of 2023, contributing around 3% of electricity. Targets. Expand to 22,480 megawatt by 2031. Thorium advantage. With the world's largest thorium reserves, India's research into thorium reactors could revolutionize sustainable nuclear power. International collaborations, agreements with Russia, France, and the US for technology transfer and reactor construction. This mission aligns with India's goals of reducing carbon intensity and ensuring energy security for its growing population. Future outlook of nuclear energy missions. Short term, 2025-2035, expansion of SMRs and life extension of existing reactors. Medium term, 2035-2050, large-scale adoption of Generation IV reactors and hybrid nuclear renewable grids. Long term, 2050 plus, commercial nuclear fusion and full-scale thorium utilization. By 2050, nuclear power could account for 20-25% of global electricity, supporting net zero goals. Conclusion. The nuclear energy mission is not merely about producing electricity, it is about reshaping the global energy landscape for a sustainable future. Despite challenges of safety, costs, and public acceptance, nuclear energy remains one of the most viable options for achieving deep decarbonization. Nations pursuing nuclear missions are not just addressing their energy needs but also investing in a future where technology, environment, and human development can coexist. With innovation, cooperation, and robust governance, nuclear energy could well become the backbone of the 21st century's clean energy revolution.